Chapter 6, Hypothesis Tests with Means of Samples. Just as a review before we get started, I just wanted to remind you of a few terms so that you'll be kind of caught up with what we're talking about today. So a mean is an average of the scores. The population is the large group you want to know about. A sample is a smaller part of the population you study to learn about the larger group. A z-score is a standardized score that is used to compare different scores in their relationship to the mean. And our two favorite formulas, the raw score formula for the z, when you have the z, the standard deviation, and the mean, is x equals z times standard deviation plus the mean. And the formula for the z-score is the raw score minus the mean divided by the standard deviation. Okay, let's get started. So let's say we have a research study and we want to look at how to reduce stress perceived by college freshmen. Our population 1 is the treatment group, and in this group we will have 40 freshmen in a self-help discussion group. We will be looking at the mean, not the individual scores. In population 2, we will have the general population, freshmen who are not in the self-help group. And remember, we want to compare similar things, so we will need means and not scores. So how do we do this? We have to compare means with means. So let's look at population 2 for a second. Who are they? Freshmen who are not in our treatment group. How will we get information about them? Since we are comparing means, we need to get comparison samples that are the same size as our treatment sample. So we need a bunch of samples of 40. Since our treatment sample is 40 college freshmen, we need comparison samples that are 40 college freshmen, but who are not getting the treatment effect. The problem is we need more than just one. We need a whole population of them. So let's start sampling. We go out, we sample one group of 40, and then we calculate the mean. We do it again, and we get the mean. We do it again, and we get the mean. And we keep going until we have enough. And how many times is that? Is it 40 times? 100 times? 1,000 times? How would you know when it's enough? And is it easy to do that? It really isn't. And so calculating the distribution of means is what will make this process easier. Here is the simpler method. What if we could calculate the means? All we need is the mean from our sample, the spread of our sample, the standard deviation and the variance, the shape of the distribution, and our sample size. This is called the distribution of means. And I will show you step by step how we will calculate what we need to understand more about our population. So let's look first at the histograms that come from multiple samples of means. Okay, so let's say that we did that. Let's say that I sent you guys out and each one of you had to go out and do a study with 40 college freshmen. And you had to gather, it's probably going to be like a survey, maybe 20 questions, and you would get, it has to be 40 college freshmen though, okay? So you can't just go to the mall. Well, right now you couldn't go to the mall anyway, or you could, but you'd have to wear a mask and it would be uncomfortable. But you would have to find 40 college freshmen, different from the ones that your peers are going to be asking. So let's say that each of you goes out and you find your 40 college freshmen, and each of you gets a different mean, and you start to bring in your means. So here we have 50 means. Here we have 200, 400, 600, what is that, 900? 800? I can't read it. 1,000. Okay, so these are histograms where each of these is plotting the frequency of the means from each of those studies. And the more means that we have, the closer and closer our histogram starts to look like a normal curve. Do you see that? So it's one of the things that we learn about, and that one of the things that we can take for granted because of mathematical truths, that when we are investigating and doing our studies, that we are finding out by sampling part of the population, we are able to draw conclusions about the whole population. Now, one sample is not likely to be enough to draw complete conclusions, and that's why we replicate our studies. But today I'm going to show you how we draw some conclusions about populations. Okay, so let's move on. So remember in chapter 5, we looked at sample scores, we got the sample mean, and then we calculated the variance and the standard deviation. We assumed a normal distribution curve. We found a cutoff score for your preferred probability, like 95% or 99%, and we used a comparison distribution, just like in chapter 5. So that comparison distribution is when we looked at the cutoff score, and we compared the cutoff score with our z-score from our sample to see if our score was more extreme than the cutoff score, and then we could reject the null hypothesis. Remember that? Okay. This time, instead of looking at a sample score, we're going to be looking at sample means. And instead of comparing our sample score to a whole bunch of sample scores, we're going to be comparing our score to a distribution of a whole bunch of means. Okay, so I hope you're keeping up with this. As we keep talking about it, I hope that you will start to understand. I'll keep going over the concepts with you. Okay, so let's talk about some of the characteristics in a distribution of means. First, we need the mean for the distribution, and that's as you come through. One of the things that we see in a distribution of means is that the mean for a population is about the same as the mean for the original population of individuals. So the mean for the distribution of means is the same as the original population of individuals. Okay, and this will become more clear as I'm able to start showing you some pictures. Okay. The variance and the standard deviation, we've been talking about those this whole time. Now we're going to be talking about them in comparison. So we remember that the variance and standard deviation, when you're looking at a curve, that's the spread of how the distribution is spread out, how the scores are spread out across the number line and around the mean right here in the middle. And so what we find out, the difference between a normal distribution that is individual scores and the distribution of means of a bunch of samples that are means, is that the spread of the distribution of means is always less than the spread of the distribution of the population of individuals. And so what that means is that I'm going to grab a pen here so I can show you. So we have the normal curve. There's a normal bell curve where you have your mean going down the middle. When you have a distribution of means, instead of the population of individuals like this one, you would be around the same mean, but your variance is going to be very different. It's going to be a lot less, and so it's going to be a lot tighter around the mean, okay? But the shape is going to be approximately normal, and that's one of the things I was showing you with the histograms. The more means that you have, the more normal it becomes, okay? And normal meaning more shaped like a bell, okay? So let's talk about the mean of a distribution of means, okay? It's a lot of the word mean, and I know that it has been confusing for some of you, and so I just want to kind of clarify that. I have gone through my PowerPoint very clearly. I've tried to anyway, and I hope I didn't miss anything, to try to put the little m down here when I'm talking about when we're in a distribution of means. So when the little m is here, it is the distribution of means. That's what this indicates, okay? So this is not the population mean for the distribution of means. This is the actual population mean. So this is the population mean for the individual population scores, okay? So all the population scores are out there, and we have them in our big bucket of scores, and we calculate the mean, and that is our big population M. Well, what we find out is that the population mean for the individuals is the same as the mean for the distribution of means. So one of the nice things is that they're not exactly the same all the time, but they do become the same. They are close enough that when we don't know all of the details, we can estimate it by being this is the same, okay? So for the sake of our formulas for today, the mean of a distribution of means of samples of a given size, so we've got 40 going on right now. We were talking about a sample size of 40, and that's the thing. They all have to be the same size, okay? So that's where we're making the difference. The mean, where they're all the same size, the means will be the same as the population mean, okay? All right, now if you think about why that happens, it's because the selection process is random. Remember, that's one of our tenets of the way we do our experiments and our studies, is that the selection has to be random. And because we're taking a very large number of samples, eventually the high means and the low means will perfectly balance each other out, okay? So the means of a distribution of means is the same as the mean of the population of individuals. Okay, now what about the variance of a distribution of means? So variance, remember variance is SD squared, right? So the population variance on a distribution of means is equal to the population variance on the individuals, the variance of the population of individuals, divided by the number of individuals in each sample. Now remember that the number of individuals in the sample is the same. That's part of the point, okay, is that we're keeping the number of individuals in each sample the same, okay? So this is a formula for finding out what our variance is for our distribution of means if we know the variance of our population of individuals and we know the number of individuals in each sample, we can find our variance for our distribution of means. Okay. Once we know the variance, we can also find the standard deviation. The standard deviation, remember, is the size of the z-score. Remember, and we'll be talking about it again. I don't mean to confuse you, but the standard deviation is how far a score is from the mean, okay? And so the standard deviation of a distribution of means is the square root of the variance of the distribution of means. Okay, so there's the variance right there. We just calculated it on the previous screen, and it's just the square root, right? And it makes sense. There's our m, there's our, SD squared, that's variance. It's the same thing, just like old math. Okay, now one of the things that they do also tell us is that the standard deviation of a distribution of means is also known as, here's its alias, standard error of the mean. This tells you how much the means in the distribution of means deviate from the mean in the population. Okay, this is the population of individuals. So this is how much error there is. Remember, I told you that we would be estimating the mean from the population. This is an estimate of the error, but this is also why the distribution of means is so narrow, more like a tower than a hill, okay? And that's why, because it's going to be, the standard deviations are going to be much, much smaller, and everything is going to be much closer to the mean. Okay, so as we go on, it'll become more clear. Now, the next thing we need to know about our distribution of means is the shape of the distribution. The shape of a distribution of means is approximately normal if one of two things happens. If each sample is of 30 or more individuals, or if the distribution of the population of individuals is normal, okay? A distribution of means tends to be symmetrical because lack of symmetry is caused by extremes. And remember, we lose those extremes when we're doing a distribution of means. And since there are fewer extremes in a distribution of means, there is less asymmetry. And so we become much more symmetrical, which means it becomes much more normal. And again, I show you the histograms. As we increase the number of sample means, the histogram shape becomes more normal, like a normal bell curve, okay? Now, one of the things that I would think here, thinking about this, if I always want my shape to be normal and I don't know the distribution of the population, then I would always have a sample of 30 or more. That's kind of would be my rule, you know? So that's something to think about. Okay, so let's talk about these rules. And I was just going through them. I just didn't tell you they were the rules. You probably recognize them from reading the chapter yourself. So we have the rules. Rule 1, the mean of a distribution of means is the same as the mean of the population of individuals. And here we have the population M sub M is equal to the population of M, the population of individuals. Rule 2A, the variance of a distribution of means is, that's equals, the variance of the population of individuals divided by the number of individuals in each sample. And this shows you how our variance gets so much smaller. And we'll be looking at that when we make some calculations in a few minutes. Rule 2B, the standard deviation of a distribution of means is the square root of the variance of the distribution of means. And that makes absolute sense because this is squared. And it's the squared standard deviation. So to get the standard deviation, we need to take the square root. That's pretty simple. And then rule 3, the shape of a distribution of means is approximately normal if each sample is of 30 or more individuals, or the distribution of the population is of individuals is normal. Okay, I want to show you a couple of things about the shape first. So let's look at the shape. So this is what I wanted to show you. Distribution of the population of individuals is that traditional normal bell curve, okay? But the shape of a distribution of means is much tighter. Do you see that? And so what we're seeing in these comparisons, we see rule 1, they have the same mean. They're right there along the same line. But rule 2A shows that they have less variance. There's much less distance between the extreme scores and the mean, okay? And then we see that the shape is still normal. Even though it is tighter around the mean, it is still a normal curve, okay? It's not a rectangle. It's not skewed out here or skewed over here. It is a normal curve, okay? All right. So let's think about these 3 different kinds of distributions. And so I want you to kind of wrap your mind around the difference between these 3 things that we've got going on. First, we have our big population of individuals. And a lot of the information about the population of individuals are things we'll never know for sure. We infer information about our population of individuals. We can measure them, and we measure them a lot, but we'll never know for sure. But we try. Okay, so there's that. So we have our big group, and that's a big group. And then we have our samples. Okay, this is the distribution of a particular sample taken from that population. So this might be our 40 freshmen, okay? And this is a particular sample. And then this is the distribution of means of samples taken from that population, okay? So this table right here, and it is of course in your book, shows you the content, the shape, the mean, the variance, and the standard deviation for each of these types of distributions, okay? So this might be something that you jot down in your notebook to keep handy, okay? But we'll be going through these formulas as we go through the lecture. All right, so let's work out a problem. Here we have a sample situation. I'm just going to give you an example. We have a distribution of scores of large numbers of individuals on certain widely used intelligence tests. And the distribution of scores is approximately normal with a mean of 100 and a standard deviation of 15. What would be the characteristics of the distribution of means for a sample of 25 individuals? So from this information right here, and this is similar to what's given in the homework, what do we know about this distribution? We know that this is a normal population of individuals, okay, that we're talking about. And this is the information we have so far. And we're going to get information about our distribution of means from this information. Okay, so from this population, we have the mean is 100, the standard deviation is 15, and the N, the sample size, is 25. What do we need to calculate? Remember, we're trying to find the characteristics of the distribution of means. Okay, the things we need to calculate are the mean, the variance, the standard deviation, and we need to figure out the shape, okay? So let's look at these and see how this will work. All right, first things first. I've noted that we have an N of 25, but notice now we're focused on the distribution of means, okay? So let's focus on the first one. We need to follow the rules. Remember, we've talked about the rules to calculate the information. And remember, trust me, this is easier than running hundreds of studies. I've run hundreds of studies. They're long and tedious. I've done them on paper and I've done them on computers. And boy, they are long and tedious. So let's see how this goes. This is a lot faster. All right, first, the mean. What do we know about the mean? Well, the mean of the distribution of means is the same as the mean of the population of individuals. They gave us the mean of the population of individuals, therefore we now know the mean of the distribution of means. Simple. Since the mean of the population is 100, the mean of the distribution of means will also be 100, so mean sub m for the distribution of means is equal to 100. Perfect. All right, check. We've got our first rule set. Number 2, variance. SD squared for the distribution of means. Population of the population variance, or SD squared, for the distribution of means is equal to the population of individuals variance divided by n. Okay, so remember that we were looking at the population SD, so we need to get squared. All right. I don't know if this m belongs here. What do you think? Do you think this m belongs here? This m does not belong here. In your notes, do not put the m here. I'm going to grab a pen. I'm going to grab a white pen, and I'm going to cross this out. Cross that out. Cross, 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 cross that out. Cross it out. No m there. Why? Why? Because this is from the population of individuals, not from the distribution of means. See, I was going through my notes really carefully and I missed this one. It's easy to do, isn't it? Okay, So let me grab my laser pointer. Okay, I got my pointer back. Now, let's continue. So our standard deviation from our original population was 15. So the variance for our original population is 15 squared, and that is 225. So we'll put that up there, 225, divided by n, which was 25, equals 9. So the variance for our distribution of means is 9. Okay, so let's plug that back in over here. So this m belongs there. That m is a belonging thing. Now, next one, standard deviation. Standard deviation of means is, this is correct because we want the population variance of the mean square rooted, right? And so our population standard deviation of the distribution of means is a square root of 9, which we had just found, right? And so the square root of 9 is 3. So remember, the standard deviation for the distribution of means is also the standard error of means. Okay, let's fill that one in. So we're filling in our information one by one, right? So we've got our mean for our distribution of the means is 100. Our variance for the distribution of means is 9. Our standard deviation for the distribution of means is 3. What is the shape? The shape of a distribution of means is approximately normal if either each sample includes 30 or more individuals. This one does not. Our sample only includes 25, but originally we were told that the distribution of scores in our number of individuals is approximately normal. And so we can assume that the shape of our distribution of means is also normal. Okay, remember the distribution of means is normal. Okay, good. So we've got our rules. I told you this would be easier than running hundreds of studies. Are you following along now? Does this make a little bit more sense? I hope so. Okay, now we're going to look at how to calculate some z-tests bigger than z-scores because we're doing a z for the means, okay? But I just wanted to remind you of our z-score formulas. Okay, so remember hypothesis testing from chapter 5. So we restate the question. We have a research hypothesis. We need a research hypothesis and a null hypothesis about the population, okay? Which means we need to identify the populations. Step 2, determine the characteristics of the comparison distribution. Step 3, determine the cutoff sample score on the comparison distribution at which the null hypothesis should be rejected. That was step 3, right? Step 4, determine your sample score on the comparison distribution. And step 5, decide whether to reject the null hypothesis. So let's see how we're doing. All right. So a z-test is very similar to a z-score. It is a procedure we use to compare a single sample mean with a population mean when the population variance is known. So if you do know the population variance, then you are able to do a z-test, okay? So you want to determine the likelihood that a sample mean, the size of the one you obtained, could be selected if the null hypothesis was true. Okay, and so you want to see if your z-score, if your single sample mean z-score is more extreme than your cutoff score so that you can reject the null hypothesis. Okay, so if you had a sample mean of 25, m equals 25, a distribution of means with a mean of 15, so population m sub m is 15, and a standard deviation of 5, population SD sub m of 5, okay? The z-score, so you fill it all in, 25 minus 15 is 10 over 5 equals 2. So your z-score here would be 2. Okay, so that was just an example of how to calculate a z-score with means. It's very similar to those z-scores with scores. Okay, so let's talk about a hypothesis testing example. Here we have another study. In this study, a standard school achievement test is given to 64 randomly selected high school juniors. The test is given in the usual way, except that they add to the instructions a statement that students are to answer each question with the first response that comes to mind. When given in the usual way, the mean is 200, the standard deviation is 48, and the distribution is approximately normal. So from this information, we have the sample size N is 64, the population in general is M is 200, the population standard deviation is 48, and we have a normal distribution. And so this is the description or the characteristics of our population of individuals, because we have given this test before. We know that these are the results when this test is given in the usual way. Okay. Now, step one for hypothesis testing, we need to identify our populations, and we need to restate the question as a research hypothesis and a null hypothesis about the populations. So our target population is population 1, high school juniors who get the special instructions. Population 2 are high school juniors in general who do not get the special instructions. Okay, so our research hypothesis says that the mean of population 1 scores will be higher than the mean of population 2 scores. And the null hypothesis is that the mean of population 1 scores will not be higher than the mean of population 2 scores. Okay, pretty simple. Step 2. Now we're going to determine the characteristics of the comparison distribution. And now this is when we're going to be looking at and calculating the distribution of means of samples of 64 individuals each. So remember, we didn't have that information. We're not going to go out and sample groups of 64 people, okay? We have this information about our general population, and so we can calculate the distribution of means knowing this information. Okay, so from this information, what do we already know about the distribution of means? We know that the sample size N is 64. We know that the population mean is 200, and we know we have a normal distribution. So this is what we already know. Step 2, determine the characteristics of the comparison distribution. And so I've stated the given information, what I just told you, okay? But now we need to start calculating some information, okay? So here we have some good information, and I need to look at this. This is correct. Okay, so we have the population variance is equal to the standard deviation squared. So we have our population standard deviation is 48. So our population variance is 48 squared, which is 2304. There's our variance. Okay. Our population variance for the distribution of means, sub m, is equal to the population variance, up above, 2304, divided by our n, which is right up here, 64. So our population variance for the distribution of the means is 36. So population variance sub m. Now, our population standard deviation sub m for our distribution of means is the square root of our variance for the distribution of means, which is just the square root of 36, which is 6. It's nice when they're easy like that. Okay, so we are already gathering a lot of information. We have the given information and we have the calculated information. The population sub m details are the calculated characteristics based on the given information about the distribution of the population of individuals. So we were given that information and we can draw conclusions about our distribution of means. Okay, notice the differences in the standard deviations. Do you see that? 48 in the distribution of individuals compared to 6 in our distribution of means. Very different. And so I wanted to show you the difference in those shapes. So you've seen these shapes already, okay? So in the shape, when the SD is 48, it's going to be the normal curve, and that would be the population of individuals. But in a distribution of means, we have a standard deviation of only 6. And remember that standard deviation is how big the gap is between each z-score on the number line going across the bottom. And that's why these shapes are so different. It's because of the standard deviation. Okay, so remember the example. We had an N of 64. We had a population of the distribution of means of two. No, this was the population. The population mean, sorry. The population mean was 200, and that was also the population of the distribution of the means, 200, okay? We had population variance for the distribution of mean was 36, and the population standard deviation for the distribution of means was 6. We know these characteristics about the distribution of means. Okay, so this is our example. We're going to move on to step 3. Step 3, determine the cutoff sample score on the comparison distribution at which the null hypothesis should be rejected. So we're going to use the standard 5% significance level. This is a directional hypothesis, so we're going to be looking at the top 5% of the comparison distribution, okay? So we're going to be, if we have a curve like this, and we're over here, and we've got our curve doing this, we're going to be looking in this area, okay? We want our score to be over here in order to reject the null hypothesis. All right, so using the normal curve table, we find out that the cutoff score for the 5% mark starts at a z-score of plus 1.64, and so that is our cutoff score, okay? All right, so we've got our cutoff score. Step 4, determine your sample score on the comparison distribution. So now we have to figure our z, okay? In this example, the mean of the sample was 220. Calculated the z-test, that is, since it's a mean, we use a z-test instead of the z-score. They're kind of used interchangeably, just make sure that you're using the right pieces of information in the score. So we have our mean of the sample, which is 220. We plug that in here. We have our population mean over here, and that's 200. So 220 minus 200 is 20 divided by 6. So we have 220 minus 200 divided by 6. 20 divided by 6 is 3.33. This is our sample score on the comparison distribution. Okay, now we decide whether to reject the null hypothesis. Step 5, to reject the null hypothesis, our sample z-score must be higher than the cutoff score of 1.64. Our sample z-score is 3.33, so we can reject the null hypothesis, and this is when rejection is very good. Results of the study are statistically significant, that's easy for me to say, at the p less than 0.05 level, because that's the 5% level, okay? All right. Conclusions. A couple of things we know here. High school juniors who received special instructions to answer each question with their first response that comes to mind performed better than their peers. Among high school juniors, like those studied, the special instructions improve test scores. Now, of course, this is fictional. This is a fictional study, but that sure is interesting, and it sounds like a neat study. I would be curious about it. But these are the different actual distributions of a sample like this, of a study like this. So here we have at the bottom our actual samples distribution. And so we've got the mean of 220, the n of 64, compared to our distribution of means. And we find that our score is way up here, and we are definitely above the 5% level. So it is a significant result, and it is above the cutoff mark. Okay, so this is that distribution of the population. Just to kind of reiterate the differences between these groups and the distributions. Okay, now in research articles, you won't see z-tests very often. Sometimes if you do see them, it will be like this one, z equals 1.09, comma ns, where ns means non-significance. And they do that to show that the groups that they're comparing are similar. So you're not going to see those very often, but sometimes you might. We will sometimes see the standard deviation of the distribution of means used as a standard error or standard error of the means, and they're shown as the error bars. And the error bars are these lines in a bar graph. And so I pulled this off the internet, but it was one of the things where it shows these are 5 groups reported. The bar heights represent their means, but the black error bars show how the individual observations are dispersed around the average. So it appears that the measurements in group B are much more precise because they're really close around the mean than they are for group E. So these are just really spread out there. And you can see that these 2 groups were much more accurate, much closer to the mean than these 3. Okay. Now, what do we know now? We can calculate the characteristics of the distribution of means based on knowing the following. If we have the mean, the spread, standard deviation, and variance, the shape of the distribution, and the sample size, we can test our hypothesis with a z-test and decide whether to reject the null hypothesis. But how accurate are we? Can we be sure? And one of the things that I pointed out to you in the last chapter is the type 2 and type 1 errors. One of the things I wanted you to remember from that is that you can never know for sure if you've made an error. And so because we do not know for sure if the null hypothesis is true, we can only test it and test it and test it again. And so because of that, because we'll never know for sure if the null hypothesis is true, we can only show that our evidence gives us support to reject it, okay? So we can reject it and reject it and reject it. The more we reject it, the more support we have for the belief that the null hypothesis is false, but we can never prove that it's false. Okay. So let's talk about confidence intervals. Now, the example that I gave you before, we knew the population mean, but what about when we don't know the population mean? In our example, our sample mean was 220, but what if we didn't know that the population mean was 200? What if the population mean was unknown? The best estimate of the population mean is the sample mean. So remember how it went backwards we started with rule number 1 was that the best estimate of your distribution of means, the best estimate of your mean was the population mean. If you don't know the population mean, your best estimate is your sample mean, okay? So it's okay. It's okay to estimate based on that mean, okay? How accurate is it? It's as accurate as your standard deviation, okay? And that's one of the reasons why your standard deviation of the distribution of means is also called your standard error or standard error of the mean, okay? And so in our example, your standard error was 6, okay? That's actually pretty small. That's pretty small when your mean is up at 200 and your error is only 6. We're going to be calculating what our confidence is in our knowledge of what the mean might really be. Okay, so remember back in chapter 4 when we were looking at the percentages in a normal curve. So just to refresh your memory, we have the z-scores going along on the number line down below. We've got our normal curve. Remember, a z of 0 is the mean. A z-score of +1 or -1 is 1 standard deviation away from the mean. And between them, they hold 34% on this side and 34% on this side of all the scores. And then we get out to a z-score of 2 to the z-score of 2 out here. And then it includes all of this right here. Okay, so keep these in mind as we talk about our confidence intervals, okay? So we're going to look at the range of possible means that are likely to include the actual population mean. So remember, now we're thinking about our actual population and we're thinking, do we really know what the population mean is? So we have our sample mean of 220. We have our standard deviation of our distribution of means, which was 6. And let's say that we want to estimate that the actual population mean is between the z-score of -1 and a z-score of +1. Then we could say that we are 68% positive, that 68% confident that the actual population mean fits in between these, okay? If we were to expand that and go out to the two z-scores, -2 to +2, then we would be 96% positive. That would be 14 plus 34 plus 34 plus 14, okay? That the actual mean is somewhere in here. So we think about that range, and this helps us to start thinking about our confidence interval, the interval where we're confident of where the actual mean might be. And so we call these confidence limits. We have an upper and a lower value of a confidence interval. And all of a sudden I see all these numbers up here, and I'm just going to talk you through it, okay? It's a range. An interval is just a range. So I showed you the z-scores of plus or minus 1. The lower limit would be our mean minus the standard deviation, which is 220 minus 6, which is 214. The upper limit would be 220 plus 6, which is 226, okay? And so the percentage under that curve would be 68%. So I'm 68% confident that the actual population mean is from 214 to 226. If I were to move down to the z-scores in the 2s for plus or minus 2 z-scores, then the lower limit would be our mean, 220, minus 2 times the standard deviation, so that would be minus 12, equals 208. That's the lower limit. The upper limit would be 232. And the percentage under this curve would be 96. So I'm 96% confident that the actual population mean is between 208 and 232. Now you'll notice we don't use 68 or 96%. We use 95 or 99% in our confidence levels. And so remember our significant levels, that's the same kind of thing. So I want to show you how you can calculate the confidence levels, confidence intervals for 95% confidence intervals and 99% confidence intervals for these z-scores. Remember when you were looking up those z-scores over and over and over again in that table? Okay. Because we like to use standardized scores, you can jot these down in your notes, because the z-scores for the 95% confidence level, or for p equals 5% or 0.05, is 1.96, negative or positive. For 99% or 0.01, if you're talking about it for the probabilities, it would be 2.58, negative or positive, Okay, so these are the z-scores. You were looking those up over and over again so you could become familiar with that percentage amount that's under the curve. But now you know where these numbers come from. Okay, so confidence. A distribution of means, and the 68%, 95%, and the 99% confidence intervals for high school juniors taking a test with special instructions. Okay, so here we are. We are 99% confident that the actual population mean falls between 204.52 and 235.48. How did we get that number? Let me show you how that happens. There is a process for figuring your confidence intervals, and we've already calculated a lot of these things, but just so that you have the formulas in your notes, you need to have them. So remember that your best estimate of the population mean is the sample mean. So step one, estimate the population mean and figure the standard deviation of the distribution of means. So your SD of sub m. Okay, so that's your distribution of means. So you find your variance of your distribution of means, and then you take your square root of that to find your standard deviation. Okay, so these are the correct formulas. That is supposed to be sub m because that is not sub m. Okay. Now, remember the example. We had an N of 64. Our sample mean was 220, and our sample standard deviation distribution of the means was 6. So these are the results of our study. Figuring the 95 and 99% confidence levels. Step 2, find the z-scores that go with the confidence interval you want. For 95, the confidence interval z-scores are negative 1.96 and positive 1.96. For 99% confidence interval, z-scores are negative 2.58 and positive 2.58. I like to put them in this order. Sometimes I've seen them reversed where the positive goes first, but I noticed that, and it makes more sense to me anyway, and maybe it will to you too, that the negative is where the lower limit will be, and the positive is where the upper limit will be, and that will put your calculations in the right order so that you will have the lower limit and then the upper limit. Okay, so let's do this bad boy. Do you see this? Step 3. Now you're going to change your z-scores to raw scores. Okay. All right, so here we go. We have our z-scores. Those are the for the 95% confidence interval. We have the lower limit is negative 1.96 times our standard deviation for the distribution of means plus 220, which was our mean. So we have 208.24. The upper limit, same thing, only with the positive 1.96, and we get 231.76. So the 95% confidence interval is 208.24 to 231.76. We do the same calculation for the 99% confidence interval, only this time it's 2.58 negative and then positive for the lower and upper limits, and we get 204.52 to 235.48. Okay, so let's just say we're going to be extremely conservative here, and we're just going to say, look, the population mean has got to be, I'm 99% sure that the population mean has got to be between 204.52 to 235.48. Okay, it's got to be in there. If it is not in there, if our general population is not, if the general population mean is not in there, what does that mean? That means that my sample of my juniors who took this test with the special instructions, maybe they really did do better. So maybe we could use this confidence interval as a hypothesis test. So look at this. When we do know the mean for the general population, and we're not just guessing, we can actually use the confidence intervals for hypothesis testing. So in the high school junior study, our 99% confidence interval for those who got the special instructions was 204.52 to 235.48. The mean of the population that did not get the special instructions for population 2 was 200. That is outside the range of our confidence interval. That means our guys did better than their guys. And if the confidence interval does not include the mean of the null hypothesis distribution, then our result is significant and we can reject the null hypothesis. So you can actually use confidence intervals as hypothesis tested. It's just another way to kind of check your work. All right. Now, in research articles, you will often actually see confidence intervals, and you'll see confidence intervals in the recent elections, in the polling data that they give you. They'll sometimes give you confidence intervals that show you how confident they are that their estimations are accurate. And so it's kind of like an error message. They're just like, well, we might have been, we say that, like this researcher explains that the average amount of overtime hours worked is 3.7 with a 95% confidence interval of 2.5 to 4.9, which means that the true amount of overtime hours is probably somewhere between 2.5 and 4.9. We're 95% sure it's about this, but probably between these two, okay? And that's a confidence interval. And this is more of showing you that this is not an exact science. This is psychology. This is social and behavioral sciences. And so we do the best we can with the numbers that we have, and we make estimations and we replicate the work. I really do hope that this helps you guys to understand how to do these calculations so we can get through the rest of our few more chapters that we have left. All right, you guys, enjoy.